Hello students, welcome back to another lovely tutorial class, and today we want to look at a very important topic in physics, which is heat energy. Now, before we go into this class, I would like to advise you guys to ensure you don't skip any part of this video. And ensure you watch this video from the beginning to the end. We have a lot of things we'll be doing here. I'm sure you don't something like distract yourself by any means. Just focus on at the end of the day, your knowledge will something like be increased. So let's go into this class, which is heat. What is the meaning of heat energy? What is the meaning of heat? Heat is a form of energy that brings about the sensation of warmth from some textbook, but I will be defining heat in this form that heat is an energy. What is the meaning of heat? I said heat is an energy. That means heat is actually an energy. Yes. What's energy? Energy is the ability to do work. That's energy. So that's why we have example of energy, types of energy to be heat energy. Heat is an energy that can move from one place to another due to temperature difference. Heat is a form of energy that can be transferred from one point to another due to temperature difference. So that energy that can move from a region to another region because of their difference in temperature is what we call it heat energy. What do I call it? We call it heat energy. Now, we're going to be studying this heat energy in two forms. There is one that is specific, and there's another heat. Now, we are going to have two forms of heat in this class. Now, we have the heat that can alter the temperature of the body. That is, if you remove it from the body, the temperature will be reduced. If you add it to the body, the temperature will be increased. We have that heat. Then we have the heat that if you either remove from a body or give to a body, the temperature will remain the same. There are two heats I'm going to be looking at now. Now, the other one that will not alter the temperature of the body is what we call it latent heat. We're going to be looking at specific heat. We'll also look at latent heat. Now, let's move to specific heat. Now, what is the meaning of heat capacity of a body? I said we have heat capacity of the body. We have specific heat capacity of the body. We also have the molar heat capacity of the body. Now, what's the meaning of specific heat capacity? What's the meaning of heat capacity? What's the meaning of molar heat capacity? Now, the heat capacity of a body, I will denote that by Cp. The heat capacity of a body is the quantity of heat required to raise the temperature of a body. Requires to raise the what? The temperature of a body, and that by 1 degree Celsius or 1 Kelvin. Requires to raise the temperature of a body by 1 degree Celsius or 1 Kelvin. So this heat capacity is the quantity of heat required to change the temperature of the body. That's what? Any heat you will need to change or to raise the temperature of the body is called heat capacity. It's called what? Heat capacity. So from here I will say something like heat, okay? This Cp means heat capacity. Q means the quantity of heat. Q means heat, energy. Then the theta means change temperature. Then from here I will just say C is equal to Cp change in theta. So this Q is called heat energy or heat. Then Cp is heat capacity. Then the theta, change in theta is theta 2 minus theta 1, which is change the temperature. So the unit of this Cp, the unit is in joules per kilogram, or you can say it's joules per Kelvin or joules per degree Celsius. Any of the two will be correct. Is either in joules per kilogram, joules per Kelvin, not kilogram. Sorry about that. Is either in joules per Kelvin or joules per degree Celsius, depending on the temperature you are using. So most persons will just give it as joules per Kelvin. So you can also put it there as joules per degree Celsius. You're also good to go, depending on whether you're in Kelvin or you're in degree Celsius. Because changing temperature in Kelvin and degree Celsius will be the same thing. So you take note of that. Now, what about for specific? We said heat capacity is the quantity of heat required to raise the temperature of a body, either by 1 degree Celsius or 1 Kelvin, or they raise the temperature of a body. Raise the temperature of a body. Now, what is now specific heat capacity? Now, the definition of heat capacity and the definition of specific capacity are almost the same thing. But there is something that will change or alter or that will come on board in this specific. Now, the specific heat capacity, I will just denote it by C. By C. So some people will call it the SHC, which is specific heat capacity. But I will write it as C now. The specific heat capacity of a body, C, is the quantity or the amount of heat required to raise the temperature of a unit mass. You see, for this specific capacity now, mass is now coming on board. But for heat capacity, I did not mention anything like mass. To raise the temperature of a unit mass of a body, either by 1 degree Celsius or by 1 Kelvin. You can just say the specific heat capacity of a body is the amount of heat required to raise the temperature of a unit mass of a body or of a particular mass of a body. So the temperature you require to raise the temperature of a specified mass of a body is called specific heat capacity. In this case now, I will give you, look at the mass of this body we are talking about. We are not talking about water. I'm not asking you how much heat you require to raise the temperature of water from 10 degrees Celsius to 50 degrees Celsius. No. I will mention the mass of water I'm talking about in this case. But in this case, there's no need of mentioning mass. Mass will not show up here. I'll just ask you, how much heat do we need to raise the temperature of a block of ice or to raise the temperature of water? I'll just mention water arbitrarily from maybe 20 degrees Celsius to 50 degrees Celsius without mentioning the quantity of water. I'm actually asking the temperature to raise its heat. Now, in this other case, I will mention the amount or the quantity of water or the mass of that water I'm actually talking about. I will say 10 grams of water, 50 grams of water, and so on. I'll measure the mass. So in this case now, mass will come above for specific quantity, but for this quantity, mass will not come above. So this is equal to the quantity of heat required to raise the temperature, that is the theta, of a mass M. So in this case, if I want to make Q is a formula, Q will not be equal to this times this, now be MC change theta. MC what? Change theta. So MC change theta. So this one is for specific heat capacity when mass is given, while this other one is for heat capacity. Let us go back. So heat capacity and specific capacity are not the same. Now, what is the relationship between heat capacity and specific heat capacity? What is the relationship between heat capacity and specific heat capacity? The relationship would be, look at it. Now, heat and heat energy. Look at the unit of heat energy. Q is the heat energy here. This Q is called, all the Q's you are saying are heat energy. The unit is joules, that's the unit. Joules, just as unit for work. Now, look at it. The unit of mass is kilogram. Then, what about the unit of C? What is the unit of C? C is in, look at it, C is joules per kilogram, either per or degree Celsius, or some people say per Kelvin. So we call it joules per kilogram Kelvin, or joules per kilogram per degree Celsius, depending on the unit of the temperature unit you are using. Just as I was mentioning for this, whether I use joules per Kelvin or joules per kilogram, joules per degree Celsius. This one don't have anything called kilogram for heat capacity. Take note of that. Now, look at something. Now, since this Q is always in joules, that means this Q and this other Q are the same. This Q in terms of heat capacity is equal to this. This Q in terms of specific capacity is equal to this. So this Q, since Q, which is here, is also the same thing as this other Q, we just say this and this will be the same, which is what? Cp change theta will be the same thing as MC change theta. So change theta will cancel change theta. So that heat capacity will be equal to mass times specific heat capacity. That is number one. Number one. Then take note of this. Then from here on you can make mass, the solve the formula. Mass will be equal to divide both sides by C. Cp over C. That is specific heat capacity. That is heat capacity divided by specific heat capacity. For example, also make this specific capacity formula. Specific capacity will be equal to Cp over N. That is Cp divided by mass. That will also give you specific heat capacity. So take note of this and this. I can ask a question. You can ask a question and just say, okay, let's say, okay, let me give you guys let's look at two questions now. What is the mass of an object or a body? What is the mass of a particular body? What is the mass of a particular body whose specific heat capacity is 480 joules per kilogram per Kelvin? Whose specific heat capacity is 480 joules per kilogram per Kelvin? And heat capacity is 100 joules per kilogram. And heat capacity is 100 joules per kilogram. What is the mass of the body? What is the what? What is the mass of the body whose specific heat capacity is 480 joules per kilogram Kelvin, and heat capacity is what? 100 joules per kilogram. So we said the mass of that body would be the heat, that is heat capacity divided by specific capacity. Now what is the heat capacity? 100. What about the specific heat capacity? 480. This will cancel this. So 10 over 48. What are we going to have as an answer for that? Divide 10 by 48. So the answer is going to be 0.21 kilogram. That will be the mass of that body. That will be what? That will be the mass of that what? Of that body. Now let's look at another question. Calculate the quantity of heat. Calculate the quantity of heat required to raise the temperature of 10 grams of water. Requires to raise the temperature of 10 grams of water from 20 degrees Celsius to 50 degrees Celsius. Calculate the quantity of heat required to raise the temperature of 10 grams of water from 20 degrees Celsius to what? To 50 degrees Celsius. In bracket, assume SHC for water. Assume SHC means specific heat capacity for water to be equal to 4,200 joules per kilogram Kelvin. Assume the SHC for water to be equal to 4,200 joules per kilogram Kelvin. Now the solution will be, is going to be that the quantity of heat required to raise the temperature of a mass, the body, is equal to MC change what? Theta. Now, what is the change in theta? What is change in theta? Change in theta is from 50, 20, that gives us 30 degrees Celsius. Then, what about someone say, this one is in Kelvin, that's what I told you before. So now you either put it in degrees Celsius or in Kelvin. If you convert this one to Kelvin, if you still find the change in temperature, it will still be 30 Kelvin. It will still be the same thing. So that's why even though it's in Kelvin, this one is in degrees Celsius. For heat, as far as change in temperature is involved, we'll just solve. We'll still have the same answer. Then, what about for mass? Mass is equal to 10 grams. 10 grams, which is, this one is a kilogram. So I have to lose on to kilogram by divided by 1,000, because 1,000 grams is equal to 1 kilogram. To convert from grams to kilogram, divide by 1,000. That's going to give us 0.01 kilogram. That's what we're going to have. It's 1, 2, 3. That's 0.01 0.01 kilogram. So the quantity of heat now will be equal to mass, which is 0.01 times specific heat capacity for water. We said it's going to be 4,200 times change the temperature, which is what? 30. That's going to give us 12,260 joules. That's what I'm going to have. 1,260. 1,260. Or 1,260. That's what I'm going to have as our quantity of heat. This is the quantity of heat required to raise 10 grams of water from 20 degrees Celsius to 50 degrees Celsius. You can also confirm this in your calculator to see it will be the same thing. Now, let's look at method for measuring the specific heat capacity of a body. Method used if you want to measure the specific heat capacity of a body. Now, the instrument used if you want to measure the specific heat capacity of a body is the instrument called calorimeter. Calorimeter. Now, calorimeter is also an instrument used for measuring heat, energy, and we have some methods we use to measure the specific heat capacity of a body. Number one, we can use electrical method. Number two, we can use method of mixture. Method of what? Mixture. Then we can also use continuous flow method. Continuous what? Flow method. Now, we are going to be running through these three methods, and the case may be as you are going, please you move with us. Now, method one, electrical method. Now, when measuring the specific capacity of the body, there is a particular model or rule or law we are going to follow, which is the heat loss by a body must also be equal to heat gain by an equivalent body. So, if a body is losing heat, another body will be gaining the heat. That is the rule we are going to be following here. Heat loss is equal to heat gain. Now, we all know that in electric energy or in electricity, there's something we call electric energy. And we say this electric energy, we are doing electrical method. This electric energy is equal to, so the electric energy is equal to, this one is electric, we use E for electric field. So I will still use Q for electric heat energy now. Now, Q for electric energy will be IVT. I don't know if you can remember that, which is power times time. Or it's also stated as I square ROT. So it's stated as I square ROT. Or power times PT. Power times time. And so on. Then, from this place, the specific heat of a body, energy from specific heat is MC change theta. Now, this is the heat energy required to raise the temperature. For example, now, if your hand is hot, the heat energy you are feeling from your hand is this. Now, if you look at your bulb, if the bulb is hot, the heat energy you are feeling from the bulb can be measured by this means. Because these are the things producing the heat. Now, your hand now, we have this producing the heat there. We have the mass, your hand has mass. Then it has every component of the hand has specific heat capacity. Then there's a change in temperature also going on. For example, let's say you have a spoon. Let's say you have a spoon, you place the spoon on top of a hot sauce. Then you remove the spoon from the hot sauce. You know that because it's a metal, you have conducted heat, it will not be hot. Now the heat gained by that metallic spoon can be measured by this means, not this means. Reason because that metallic spoon has a particular specific heat capacity. Then it has the mass there. You can measure the mass. Then there's a change in temperature that goes. So they can measure that amount of heat gained by that hot spoon. But when you go to electricity, this is how you measure heat energy from any electrical source, whether it's your hot plate, whether it's your rig boiler, and so on. This is how you measure their electric, the heat energy coming out from any electrical source. You measure it this way. Now, if you want to now check for the specific capacity of a particular body, now we can have solid. We can also have liquid. Now, when I was doing expansion, I told you guys that that you cannot heat up a liquid if you are not keeping the liquid inside a vessel. Now, if you are looking at a solid, you cannot place solid anywhere and start heating it. You can place solid anywhere. You can plug your ring boiler and allow it to something like hot. You can even put it on top of something red hot. If you are not putting it anywhere, as long as it's solid can be heated anywhere. But if it's liquid, you must place it inside something. And the stuff we use here for measuring, the container we use, we call it a calorimeter. That's the container we use for holding our liquid. We want to check the specificity of the liquid. That is why if the properties of this calorimeter or the properties of this container is given, whether you don't use calorimeter, whether you are using any other thing, if the properties are given, you will also put the properties into consideration. Now let me check for solid body. For solid body. Now let's say you plug an electrical source, then you now connected it to a solid body. You heat the solid body up. Now the energy coming from this electrical source is measured by IVT or I square RT. That's the energy coming from this electrical source. Now the heat energy that will be gained by this body here, we measure by MC change theta, because this one is a mass of a particular body, not coming from any other source called electricity. So which one will be losing heat and which one will be gaining heat? Now this body here will gain heat, then this electricity will be losing heat. So heat loss from the electricity will be IVT. That will be heat loss from this electricity. Then will be equal to heat gain by this equivalent body here. And which heat will be gained by this body? MC change theta. That will be heat gain by this particular body. So the rule we use is that heat loss is equal to heat gain. That is the rule we are using. Heat loss is equal to what? Heat gain. Now this one is going to lose heat, it is this. This one will be gaining heat, it is this. So keep this one into your mind. Anytime you are asked a question in which they will be comparing two bodies, they'll say maybe you boil water, you now put it inside tea. Calculate the quantity of heat required to raise the temperature of the tea from here to here. You will just check which of them is losing heat and which of them will gain heat. Now let me tell you something. Under normal circumstances or normal conditions, heat cannot flow from a lower, something like a region that has lower temperature to a region that has higher temperature. No. Heat always flow spontaneously or under good normal condition from region that have higher condition of temperature to region that have lower condition of temperature. But in this case now, a hot body will give heat to a colder body. So in this case now, when we are measuring this heat will flow from a hotter region to a colder region always. It will flow from what? A hotter region to colder region. So this one is hot now, this one is cold at the beginning. So this hotter region, heat will flow from here to this colder region in this body. So we now raise the temperature of this body now. This one will gain heat. That's why I'm saying this one will gain heat. This one will be losing heat. That's why when you plug an electric boiler or a hot plate, you check your meter. We saw that you check the energy that the thing is consuming. That means it's losing energy, it's using energy. It's losing energy. This one is gaining the equivalent energy. That's how the thing is. So, that's okay. What is the specific capacity of this body now? I want to make C different from what I'm saying. C is equal to IVT over M change theta. So this is how you now measure the specific capacity of this body here. Now if you know the mass and you know the change temperature, you are ready to go to measure the specific capacity. Now if it is liquid, let's say you now have liquid, something like you now have a ring boiler. Let's say you place a ring boiler like this, you just plug the ring boiler, then you now place it inside liquid. Let's say you place it inside liquid. Let's say you place it inside liquid, you have liquid here, then this is the container containing the liquid. Then you now raise the temperature of this liquid from particular. Then one thing you should know is that as the temperature of this liquid is decreasing, this container will also be gaining heat. Because if you touch the container, you discover that it's also hot. If you are boiling water using a ring boiler or hot plate, you discover that even the container or that pot you are using will still be hot. Whether it is rubber pot or metallic pot, it will be hot as far as it can conduct heat. So because of this, what we are going to do for measuring the specific temperature of liquid now, we say source that is bringing down the heat. What is bringing down the heat? What is bringing down is this electric source. And to measure the quantity of heat from electric source is I VT or I square root T. Or I square root T. Then this one will be equal to water will gain heat, and the heat gained by water will be mass of the liquid. Okay, let's just say liquid, not just any other water, not just water, let's say liquid. It can be oil, it can be any other liquid. Mass of this liquid times the capacity of this liquid times the change temperature of the liquid. Change temperature of this liquid and change temperature of this vessel here, which can be a calorimeter, will be the same. Then plus, another thing also gain it. What will gain it again? This container, which is mainly, we call it here a calorimeter. That will be mass of that calorimeter times the capacity of that calorimeter and change the temperature of that calorimeter. This temperature and this one will be the same. Ideally, it will be the same. Then, if you want to measure the specific capacity of the liquid inside now, you make this Ca, the solid formula, by moving this to this side, then you divide both sides by Ml change theta. That's what I go out. That will give you something like I Vt minus Mc Cc change theta over Ml change theta. That will be equal to Ca. That is the specific capacity of that liquid that is inside now. So that's how you check for liquid. That's how you check for liquid here. Then we also have method of mixture. For method of mixture, what you do, you will boil or heat up a solid body. The method of mixture is a solid. Heat up this solid body. Then you now place the solid body inside a liquid. You place it inside liquid. Place the solid body inside liquid. They discover that the initial temperature of this solid body, you measure the temperature of this solid body when it's now hot. You call it, let's say, theta 3. You measure the temperature of this liquid initially. You call it theta 1. Initial temperature of the liquid, you call it theta 1. Then after you have now placed this solid body that is now hot, that is hot, inside this liquid, you will allow both of them to attain a particular temperature. You know, this hot body now will raise the temperature of this liquid from where it is to somewhere, but not actually up to this theta, because this one will be losing heat, while this one will be gaining the heat. So when you know this one body is not losing heat, the other one, instead of now equilibrium will be attaining, says that this solid and liquid will be having the same temperature, and that's what you measure. We call it theta 2. The change temperature of this one will be theta 2 minus theta 1, while for this one will be theta 3 minus theta 2. So from there, you just say heat loss equal to heat gain. Now from here now, we just, which one is losing heat? If I ask you, between this liquid and this solid, which one will losing heat? The solid will lose heat, and it's going to lose heat of Mc change theta, because there's no electricity here. Now, this liquid and this vessel, which may be a calorimeter, will also be losing heat of Mc change theta. Solid, this one will be for liquid, the other will be for solid. Look at what I'm trying to do now. This will be the same thing. Then this, instead of using IVT here, since the heat is coming from a solid body, you just carry this and put it here and put solid. And just remove this one, put M solid, C solid, and Q change it as solid. Then you're not good to go. That's how it is done. Then you now make anyone you're looking for the subject of what? Of the formula. Now, there's another one, continuous flow method. Continuous flow method. Now, in 1902, Calendar and Barnett devised a means, which is an electrical method for checking the specific heat or obtaining the specific capacity of liquid at steady temperature. So that method, we call it continuous flow method. Actually, it was derived or devised or coined by the scientists Calendar and Barnett. Calendar and Barnett. What you do for me now, go and check the correct spelling for that calendar and the correct spelling for that Barnett, because it's not just anyhow calendar or year, one calendar year. No, that calendar. It's a scientific name for a particular scientist that devised, two of them devised continuous flow method in 1902, and they are Calendar and Barnett. So now, before we go into calculations, remember we have mentioned this electric method of heat capacity, method of mixture, and again, we are using this method of mixture. Just say this one will be losing heat. That is the amount of solid, so the capacity of solid, change the temperature of that solid. Remember, this one move from theta 3 to theta 2. Then it's not will now be equal to heat gain. Liquid will gain heat. This liquid will gain heat. Then the vessel will also gain heat, which may be a calorimeter. We say mass of calorimeter, C for calorimeter, change the temperature. That's what I'm trying to say. The next thing you do now, ensure you know their temperature change. This one, this we have the same temperature change. This one move from theta 3 to theta 2. So move from theta 1 to theta 2. So we just obtain them. That's all. Now, let's look at another important aspect of this class, which is another type of heat that a body will receive, especially water. We'll be using water as our case study. Remember, water can exist in three phases, mainly solid, liquid, and what? Gaseous phase. And water has three phases, which is what? Liquid, solid, and what? Gaseous phase. We have liquid, solid, and what? Gaseous phase. Water can be solid, then will become liquid, will now become form of gas. Now, if you want to move from solid to liquid, remember, what is this phase? This phase is solid. Then this one move to liquid. Let me just draw this liquid this way. Then the gaseous, this one moves to gaseous. You check now, this phase and this phase and this phase, they are not the same thing. This one is close, packed together closely. So it's somehow packed together close, but you take the shape of the container. This one is loose, can move freely, but it's the same water. Now, if you want to move, listen, I'm trying to explain something. If you want to move from solid to liquid, you discover that at a point the temperature will be maintained at 0 degrees Celsius. And at 0 degrees Celsius, this water will be solid. Automatically, it will just change to liquid. It will still be 0 degrees Celsius. Then, if you are heating up this water, if you heat up more, water will be boiling at 100 degrees Celsius. Automatically, this boiling water will just change to vapor, which is not of gas in the gaseous state now. It's not in the gaseous state. Now, that gaseous state, and this liquid state are not the same. But the gaseous state temperature and the boiling one that is still liquid, they have the same temperature. Temperature of water vapor is still, or steam. Now becomes steam. This one can be ice, water, and liquid water, then steam. You understand that one better? Now let's say ice, so it's not liquid, but it's not steam. Let me not do it like that. This one will be better. Move from ice, this, to steam. This one will be better. Now, as ice solid, we will change to liquid at 0 degrees Celsius. Then if you now heat it up, now apply heat. Now the temperature will increase from that 0 to 100. It start boiling. At that same moment, we change to steam, which is now a form of gas. Now, what amount of heat, or what happened when this water changes from ice to liquid and the temperature was still 0? Is it something like natural phenomenon for something to change phase and the temperature would remain the same thing? Or is it freely, something like this, something that is free for this to just change its phase? Is it free? It's not free. There is amount of heat energy consumed for something to change, from this water to change from solid state to liquid state. And the temperature will still be the same, yes. Now there's another heat there, yes. And this heat is what we call latent heat. This is what now something like This now will not bring us to something called latent heat. This brings us, or brings about this latent heat we're actually talking about. When something will change state, but will not be changed in temperature. Now, what is the meaning of latent heat? Latent heat is the quantity of heat required for a body to change its state without a change in temperature. It's the amount of heat either taken in or removed. The amount of heat given out or taking something that will sometimes the quantity of heat that the body will receive or quantity of heat that the body will give out when it changes its phase or when it changes its state without change in what? In temperature. For example, when it's changing from ice to liquid without a change in temperature. When it's changing from liquid to steam without a change in temperature. That heat that causes that change of state is called latent heat. What I call it? Latent heat. Now, if you check, we have two states here. From ice to liquid, from liquid to steam. Now, this one, the heat now, the latent heat. Now, we're not saying latent heat. We're not talking about something that will move temperature. No. It's not going to touch temperature. Now, the latent heat that will occur here. Alright, the latent heat that will occur here. So we're going to look at now. Now, we have two latent heat here, this and this. Now, therefore, we have two types of latent heat. The first one is the latent heat of fusion. Second one is the latent heat of vaporization. This one is what? Latent heat of fusion. The second one is what? Latent heat of vaporization. Now, what is the meaning of latent heat of fusion? Remember we said latent heat is the quantity of heat required for what? To change. Or the amount of heat either taken in or given out when the body changes its state without changing temperature over just the mass of that body. That's all. This mass will change state, it will not be changing temperature at all. The temperature will still be maintained. Then, from here now we'll just say, from here we'll say Q is equals to L to M and M times L. This is the formula for latent heat. Now, this latent heat can call this one latent heat of fusion, call this one latent heat of vaporization. Latent of fusion and latent heat of what? Vaporization. Now, what's the meaning of latent heat of fusion? Latent heat of fusion is the quantity of heat absorbed or given out. Quantity of heat either taken in or given out when a body changes from solid to liquid without changing temperature. When ice melts to liquid without changing temperature. So the quantity of heat that will melt an ice or that will melt a solid water to liquid without a change in temperature is called latent heat of fusion. And to measure that heat, Q will be equal to, this is the heat we're talking about, be equal to LF times M times LF. Or you say LF is equal to Q over M. Now we're not talking about latent heat of fusion. Latent heat of what? Fusion. Why that of vaporization? Why latent heat of vaporization is the amount of heat? The amount of heat involved when water changes from something like if you change water from boiling or from liquid to steam without changing temperature. When water moves from liquid to steam without changing temperature. So that Q will be equal to mLV. So this one is latent heat of vaporization and latent heat of what? Of fusion. So don't forget the quantity of heat requires to melt ice water to liquid, that is to melt solid ice to liquid at 0 degrees Celsius is latent heat of fusion. Why that requires to what? Convert boiling water from liquid to steam. That is the gaseous state now. It's latent heat of what? Vaporization. So before you move from, for example now, before you move from 0 degrees Celsius ice to 0 degrees Celsius water, you come across this heat, quantity of which is M for fusion. Before you move from 100 at 100 degrees Celsius, before you move from liquid to gaseous state, you must overcome this latent heat or you must have or take in, you must absorb this latent heat of what? Vaporization. Take note of that. Now, approximately for ice, latent heat of fusion for ice is approximately, let's say, 3.34 times 10 to the power 5 joules per kilogram. Now, the formula, the unit of latent heat is joules per kilogram. Take note of that. Then, the latent heat of fusion, latent heat of vaporization for boiling water or for steam is 22 point, either 5 or 0.6 times 10 to the power 5 joules per kilogram. Or you can say 2.26 times 10 to the power 6 joules per kilogram. So you please also check to see if we are already in order. Now let's look at the question. Let's look at the question. Obtain the quantity of heat. Obtain the quantity of heat. Obtain the quantity of heat requires to melt 100 grams of ice water at 0 degrees Celsius. Obtain the quantity of heat requires to melt 100 grams of ice water at 0 degrees Celsius. The quantity of that heat is what? LF. Where LF is the latent heat of fusion for ice. That quantity of heat will be equal to, remember there's no change in temperature, temperature will be maintained at 0 degrees Celsius. So what is mass? Mass there is 100 divided by 1000, that gives us 0.1 kilogram. Now take note of this. The unit of latent heat for fusion and for ice is joules per kilogram because there's no temperature here. It's just joules over N. Q, unit for heat is always joules. But for latent heat is joules per kilogram. Specific heat capacity is joules per kilogram Kelvin. Then heat capacity is joules per Kelvin. Take note of that. Then from here now, you can say the quantity of heat required to do that job will be the mass, which is 0.1 times the latent heat of fusion for ice, which is 3.34 times 10 to the power 5. This one gives us 3.34 times 10 to the power 4 joules. That is the quantity of required to melt these grams of ice at 0 degrees Celsius. Now let's look at another question. Calculate the quantity of heat. Calculate the quantity of heat requires to convert. Calculate quantity of heat. Calculate quantity of heat requires to convert. 10 grams. Okay, let me use 50 grams. We have to convert 50 grams of ice at minus 10 degrees Celsius. We have to convert 50 grams of ice at minus 10 degrees Celsius to liquid water at 20 degrees Celsius. We have to convert 50 grams of ice at 10 degrees Celsius to liquid. And will now be at what? 20 degrees Celsius. So how are we going to do this job? How are we going to do this job? How are we going to do what? This job. Now look at it. In this case, now you are just going to be very careful. Now in bracket, you can write assume specific heat capacity for ice is equals to, let's say, 2000 joules per kilogram per Kelvin. Then specific capacity of water is 4200. I've already used that. I've used that before. This one is constant. Then the latent heat of fusion for ice, that is 3.34 times 10 to the power 5 joules per kilogram. Now, one of these examples we are going to look at something. We have the mass of water to be 50 grams. Abi? Yeah. We have that to be 50 grams, which is set here as 50 over 1000, that is 0.05 kilogram. That's what I have in there. 0.05 kilogram. That is very good. Now, look at another thing. Another very important something very, very important is, look at it. And it here is that. Now, check the specific capacity of ice and that of liquid water. They are not the same thing. That means the way ice will receive it and the way liquid will receive it, it's not the same. It's not the same. So if you want to do this thing, look at what we are going to do. We are going to do the part of ice separately. Now look at it. The quantity of heat required to do this job now, to move it from here to this place will be, look at it, be equal to the quantity of heat required to convert the ice to water plus, no, the quantity of heat required to move the ice from minus 10 degrees Celsius to 0 degrees Celsius. That is the first thing. The quantity of heat required to move it from minus 10 to 0. That is the first thing. I don't want this thing to be, I'll call this one the Q1. Okay, let me just call it the quantity of heat required to raise the temperature of the ice. Then, plus the quantity of heat required to melt the ice to water. We call it latent heat of fusion for ice. Then, plus the quantity of heat required to move the water now to 20 degrees Celsius. Water to 20 degrees Celsius. That's from 0 to 20 degrees Celsius. That's what I'm going to do here. So look at what I'm saying. I'm going to calculate it. Don't forget calculate the quantity of heat required to raise the temperature of ice from minus 10 to 0. That's what we will do. Then after we have raised the temperature from minus 10 to 0, then if I move from minus 10 degrees Celsius to 0 degrees Celsius, that's the first thing I'm going to do. That's the first thing. The heat that will do this job. Then plus the heat that will melt the water at 0 degrees Celsius. That is latent heat of fusion. Then plus the heat that will move the liquid now melted by this latent heat of fusion from 0 degrees Celsius to 20 degrees Celsius. That's what I'm going to do. That's what I'm going to do. Now look at what I'm going to do here. I said the first thing, we will calculate the heat that will move the ice from minus 10 degrees Celsius to 0 degrees Celsius. That's the first thing. Then at 0 degrees Celsius will still be ice. Then plus another heat that will melt this ice to liquid at 0 degrees Celsius. That's latent heat. Then plus the heat now, when the ice have been melted to liquid now, the heat that will raise it from that 0 degrees Celsius to 20 degrees Celsius, which is this. That's what I'm going to do now. So let's go with it. Now, the quantity of heat required to raise the temperature of this ice will be MC change the theta. That will be for ice. This one is for ice. So this is C for ice. Plus the quantity of heat that will melt the water at 0 degrees Celsius, that will convert it from solid to liquid, is mass times LF. That's latent heat of fusion. Then plus the quantity of heat that will raise the temperature from 0 now, when the water will melted to 20. That's mass C for water now, the change temperature. That's what I'm going to do. That's how to calculate the total heat required to do this job. Raise the temperature of ice from minus 10 degrees Celsius to 20 degrees Celsius. That is going to give us something very nice. Now what is this one? The mass is 0.5. So mass will be the same. See. So that shows us that, look at something. If you have a large block of ice inside a container, if it melts, the mass will still be the same. It will not change. Take note of that. You see now, this mass will not change. It will still be the same thing. So I can decide to move the mass out. See, the mass will not change. So we have C for ice, change the theta, plus LF, plus C for water, change the theta. So they ask you a question to say, if a large amount of ice placed inside the container is completely melted, what will happen to the mass? It will be reduced. The mass remains the same. It will not change. So that will give us the mass is 0.5. No, that is 0.05. And 0.05, 1, 2, 3. 0.05 times this one for ice, let it be 2000 times the change temperature. Move from minus 10 to 0. That is 0 minus 10. Then plus NF for what I say is 3.34 times 10 to the power 5 plus the gallons of water, which is 4,200 times change temperature from 0 now to 20. That will be 20 minus 0. So if you do this very well, you have something very nice. You have something very nice. That's going to give us something nice. Our Q now will be equal to 0.05 times, let's say we have 2000 first, times 10, because 0 minus minus is plus 10 is still 10, plus 0.34 times 10 to the power 5, plus 4200 times 20, 4200 times 20. So if you have this now, what are we going to have in this case? What are we going to have here? Let's see. Let's try and see now. Let's check. Alright, the answer is going to be 21,900 joules. That's what you have as your answer. Now let's go to another question. An 80 kg man was observed to have a temperature of 39.0 degrees Celsius. Was observed to have a temperature of 39.0 degrees Celsius instead of the normal body temperature of 37.0 degrees Celsius. Instead of the normal body temperature of 37.0 degrees Celsius. Assume the human body, okay? Assume the body of this man, this particular man, or human body. Assume the body of this man is mostly water. Of specific heat capacity 4190 joules per kilogram Kelvin. Specific capacity 4190 joules per kilogram Kelvin. How much heat will raise this temperature by this means? How much heat will raise this temperature from this 37 to that 90? That's the meaning. How much heat will raise this temperature by this means? Let's check the heat. I'll do that. Now, this is the mass of the body, and this is the temperature we found the body instead of this. So, how much heat changes the temperature from here to here? Let's check. Q is equal to, for any body, MC change the theta. That is M is 80, is a kilogram. That times C. What is the capacity of that body? 4190. Then, that's why I said it's approximately 4200 for water. Then times change the temperature. That would be 37. That is 39 minus 37. That is 2. So if you do this, we're going to have, it's going to give you 6.7 times 10 to the power 5 joules. That's what we're going to have. 6.7 times 10 to the power 5 joules. Now this is the amount of heat that will raise this temperature of this kilogram man from 37 to 39. That is the amount of heat that will do that job. Now let's look at another question. Another good question. Look at another good question. Alright. Obtain the time taken. Obtain the time taken. Obtain the time taken for an electric heater rated 600 watts. Obtain the time taken for an electric heater rated 600 watts to raise the temperature of 16 grams of water from 25 degrees Celsius, let me just say from 20 degrees Celsius to 80 degrees Celsius. Obtain the time taken for an electric heater to raise the temperature of 16 grams of water from what? From 20 degrees Celsius to 80 degrees Celsius. Assume the SHC for water. Assume SHC for water to be equal to 4,200 joules per kilogram per Kelvin. So, solution. The heat that will do this job will be MC change theta. That is the heat we are talking about. This heat will raise this temperature from 20 to 80. Okay, now what about heat coming from this heater? So this one will not work. So what we're going to do now, we are going to consult like compare the heat from the heater and the heat inside the water. Now between this heater and that water, which one will lose heat and which one will gain heat? That's the first thing before coming to your mind. Now this electric heater will lose heat of IVT, and this water will gain heat of MC change heater. Now we are looking for time. So IV, remember power is in watts. So this one is actually power. Think of that. While this one is mass. So power is in watts. So this one I'm compared to kilogram. We have times 1,000. That is this one 1, 2, 3. That's 0.016 kilogram. That's what I'm going to have. So this power is sent here as IV. That is power. So this IV now is P. T is equal to MC change in theta. So we can just say T is equal to MC change theta over P. That will be, what is that? 0.016 times 4,200 times, what is the change temperature? From 8 to 20. 8 minus 20, that is 60. Divided by 600. If you cancel this, if you cancel this. So let's solve out. 0.016 times 420 times 6 divided by 6. This 6 will cancel that last 6. That's already done. So let's quickly look at that to see what we are going to have. To do that, you are going to have 6.72 seconds. That's the time taken for this electric heater to do this job. Now, let's look at another question. Obtain the quantity of heat requires. Obtain the quantity of heat requires. Obtain the quantity of heat requires to raise the temperature of 200 grams of water. To raise the temperature of 200 grams of water from 20 degrees Celsius to 30 degrees Celsius. Obtain the quantity of heat required to raise 200 grams of water from 20 degrees Celsius to what? 30 degrees Celsius. So the quantity of it will be MC change theta. That will be, the mass is 200 grams divided by 1000, that will be 0.2 times, so SAT for water, see for water is absolutely 4,200 times 10 temperature, 30 minus 20, that is 10. So that gives us 8,400 joules. That's what we're going to have. That's quantity of heat required to do that job. Now let's look at another question now. Alright, another question. Next question. I have another question here. The question is, if 50 grams of ice, at 0 degrees Celsius, is mixed with 50 grams of water at 80 degrees Celsius. At 80 degrees Celsius. It means with 50 grams of water at 80 degrees Celsius. What will be the final temperature of the mixture? What will be the final temperature of what? Of the mixture. What will be the final temperature of the mixture? Alright, let's go with this solution. Let's go with this. So, remember we have ice, we have water at 80 degrees Celsius. So which of them, remember we have heat loss, will be equal to heat gain. Now which one will be losing heat? The water at this, remember I told you, the one at a higher temperature will be losing heat. So this one is at a higher temperature, this one will be losing heat. And the heat lost by that body will be MC change in theta. Now which one will be gaining heat? This one is at 0, this one will be gaining heat. And which heat do ice gain? Ice means solid. Ice is always solid. Take note of that. Ice water means solid water. So the heat gained by that solid ice at 0 degrees Celsius, remember is what? What is the heat gained by solid ice at 0 degrees Celsius? Ice at 0 degrees Celsius. Latent heat of fusion, which is MN. So what I'm looking at now is, what will be the final temperature of this mixture? What will be the final temperature of what? Of the mixture. So let's go. Let's go to see what we're going to have. Now the mass, this mass and this mass are the same. So this we can, okay, let me just write it as I see it. We have 50 for water, I have 50 grams. That is 0, this one divided to another 0.05. Divided down to kilogram, 0.05. So this one is 50-50, can just cancel it out. The mass will be the same thing. The mass will be the same thing. Then, okay, let's go. Let's check what we're going to have here. Let's check what we're going to have. Now, since the mass are the same, let's just cancel it out. Then the change in temperature will now be LF over C, which is 3.34 divided by 10 to the power what? 5 divided by 4,200. Divided by 4,000 what? 200. Alright, that is change in temperature will be LF divided by C. LF, that is of fusion for ice is this. We have specific quantity of water is this. So if you divide this, you are going to have approximately 80. That's what we are going to have here. So remember this one is theta 2 minus theta 1. That is theta 2 minus theta 1. So theta 2, the final temperature is 80 degrees. We are going to have 80 degrees Celsius minus theta 1 is equals to 80. So that will be equal to, so well, let's put it out and bring it here now. We are going to have 80 minus 80 is equals to theta 1. So theta, now please, 80 minus 80 is what? 0 degrees Celsius. So the temperature will still be, the final temperature will be 0 degrees Celsius. So this 80 will be reduced to 0 degrees Celsius in this case. So think about that. That means if you put, if you drop 50 grams of ice at 0 degrees Celsius into water at 80 degrees Celsius, the ice will reduce the water to 0 degrees Celsius. That's how it is. Let's go another one. A piece of aluminium, 20 grams. A piece of aluminium, 20 grams, is dropped into a large cavity of ice. Is dropped into a large cavity of ice. Now, a 20 gram, that is a piece of aluminium 20 grams, that is at 90 degrees Celsius. Take note of that. A piece of aluminium 20 grams, or a 20 gram piece of aluminium at 90 degrees Celsius is dropped into a large cavity of ice. It's dropped into a large cavity of ice. How much ice does it melt? How much ice does it melt? Or how much ice will this piece of aluminium melt? The mass is 20 grams. Remember, there is mass is 20 grams. 20 grams, 20 grams of aluminium, piece of aluminium is dropped into a large cavity of ice, and the temperature of the aluminium was 90. So it's 10 theta, it's equal to 90 degrees Celsius. How much ice will it melt? How much ice will it melt? Remember, aluminium, which one will lose heat loss equal to heat gain. Aluminium will lose heat, the ice will gain heat. So it will melt ice until this 90 becomes 0, then we stop melting ice. Because temperature of ice, remember temperature for ice is what? 0 degrees Celsius. Remember that. That is the temperature of the large block of ice. It's at 0 degrees Celsius. Take note of that. So, what we're going to do now will be, look at something we're going to do. Aluminium is going to, before this, aluminium will keep on melting ice from 90 until the temperature will be reduced to 0 before we stop melting the ice. Because when the temperature is not the same, there's no something like heat cannot flow again. The heat will not somehow be simultaneous because they have the same heat. So the two is not the same thing. That's how it is. It's not like the heat is now the heat in the ice, the heat in the aluminium. You know, nobody is having more heat than the other. Both temperatures are not the same thing. So that's how the thing makes it. So nothing is melting and that thing. Once the temperature is 0 degrees Celsius for ice as well. So the temperature of two bodies are the same thing. So there's no, even though heat is low, the thing will still be the same, like as if it's the same thing. Just like look as if it's the same. If you move two things that have the same temperature together, you look as if heat is not flowing. Although even though the heat is not flowing, you don't look as if it's just the same. This one flow here, this one flow here. Just like you are mixing two the same liquid together. you will not observe whether it is not one is flowing to another or not, because now something like at equilibrium, both of them are now having the same heat. So what we are going to have will be what is losing heat? Aluminium. The heat is MC, change it theta. What's getting heat? The ice, which is latent heat. Because you melt ice. If the melted ice is now zero, that water, that ice that changed to water is zero. That water, that heat that converted that water to liquid, that ice to liquid at zero is latent heat, which is MLF. So the mass of ice is that will be melted. Now the that portion of ice that will melt is the one we are talking about. That will be the one that will be the one that will experience latent heat of fusion. That's the portion of ice we are looking for. And that mass of ice, we don't know the temperature of the full ice, but we know that once part of it now changes to water, changes to water. Let's say you have ice like this. Let's say you have a block of ice like this. Then you now put a piece of aluminium on top of it. Then this part now changes to water. So this part now has experienced latent heat of fusion. So even though the temperature of that liquid water is zero, so that part that has experienced latent heat of fusion, what is the mass of that part that will change to liquid? So that is which is that M. It's equal to MC, change the theta over L. M and M are not the same, we take it over LF. So the next thing, the mass is 20 grams, which is 0.02 times. So the quantity of aluminium. Now assume SHC for aluminium to be 900 joules per kilogram per degree Celsius or per Kelvin. So times 900. Some people can also use 880 joules per kilogram per degree Celsius or per Kelvin. So either use 880 or use 900. 880 is approximately 900. Yeah, free. Then times this what's it called, change temperature. Now the aluminium will move from 90 to 0 degrees. You stop. So that will be 90 minus 0. Then divided by LF. What's LF? 3.34 times 10 to the 5. So what are we going to have? So our mass will now be, if you solve this very well, we are going to have 0.00485 kilograms. If you multiply this by 1000, you have 4.85 grams. But if you use 880 as specific heat capacity for aluminium, we decide to use 880, then you will have 4.74 grams. And I just converted kilogram to grams now by multiplying by 1000. When we go from kilogram to grams, we multiply by what? By 1000. So remember what we are doing here, we are trying to know how to play with heat, to measure heat and the rest. Now heat can also be presented in terms of calorimeter. So it's easy to have heat as calorimeter, joules, and so on, but not the same, just like we have temperature in Kelvin, Fahrenheit, and so on. Alright, so just to understand what we are doing here, we are just doing just to try, we are just trying to compare or look at how to calculate specific capacity of the body, how to measure the quantity of liquid, calculate the temperature of the body, and so on. So if you have anything to, okay, let's look at this question. Let's look at this particular question. Okay, calculate the quantity of heat required to raise the temperature of a body. Calculate the quantity of heat required to raise the temperature of a body. Calculate the quantity of heat required to raise the temperature of a body. From 20 degrees Celsius to 21 degrees Celsius. From 20 degrees Celsius to 21 degrees Celsius. From 20 degrees Celsius to 21 degrees Celsius. In bracket, right? Assume Cp for that body is 100 joules per Kelvin. Assume Cp for this body is 100 joules per Kelvin. Remember, Q is equal to what? Cp change in theta. So what is CP process? CP is 100. This one is heat capacity, not specific capacity. So heat capacity was given, mass was not given. 10 is 21 minus 20, that's 1. That will be 100 joules. There's no teacher of class to do that job. In case you saw it, or maybe you meet a question of this nature, or something like this pop up, or you are maybe in an exam condition, ensure you know how to use specific capacity and heat capacity. Okay, look at this one now. Calculate the quantity of heat required to raise the temperature of 4 kg of a body. Calculate the quantity of heat required to raise 4 kg of a body whose XHC, specific capacity, whose XHC is 250 joules per kilogram per Kelvin. Whose XHC is 250 joules per kilogram per Kelvin. From 10 degrees Celsius to let's say 12 degrees Celsius. From 10 degrees Celsius to what? To 12 degrees Celsius. We said quantity of heat is equal to what? SHC was given for specific heat is MC change into time. So that will be equal to the mass is 4 grams, that is 4 kilograms, not grams. 4 kilograms, the unit of converting. The equivalent is 250. Then the temperature 12 minus 10, that is 2. So that was 4 times 250, that is 1000 times 2, 2000 joules. The quantity of heat required to do that job. So that's just what they're doing. Now, why do you not use ML, latent heat? For example, now, let's say they ask you, calculate the quantity of heat required to melt so grams of ice. So grams of ice at 0 degrees Celsius. Quantity of heat required to melt ice is latent heat. Then, for example, let's say water is boiling. So, calculate the quantity of heat required to convert, let's say, 60 grams of boiling water to steam. Want to convert a particular mass of boiling water to steam, you use latent heat of vaporization. Just it's still mass times latent heat. But that case, you not use for vaporization. Latent heat of fusion is 3.34 times 10 to the power 5 joules per kilogram. Latent heat of vaporization is 2.23, 2.24, 2.25, 2.26, and the case may be times 10 to the power 6 joules per kilogram. Joules per kilogram. That's it. Joules per kilogram. So ensure you know how to run all these stuffs. So let's look at a particular question now. Let's look at this question. If 1.13 times 10 to the power 6 joules, 10 to the power 6 joules of heat energy, if 1.13 times 10 to the power 6 joules of heat energy is required to convert 0.5 kg of boiling water to steam. It's required to convert 0.05 kg of boiling water to steam. Calculate the latent heat of vaporization of water. Calculate the latent heat of vaporization of water. So this question is, if we use this heat to convert this boiling water to steam, what is the latent heat of vaporization of this water? Remember I told you, for latent vaporization, Q is equal to what? LV, or LV is equals to Q over what? N. Which is empty as 1 Q is 1. This is the heat energy, which is Q. 1.13 times 10 to the power 6 over the mass is in kilogram already. 5. So if you do this very well, we are going to have 2.26 times 10 to the power 6 joules per kilogram. That's what we're going to have. 2.26 times 10 to the power 6 joules per kilogram. Now we are going to stop this class here. That is nominal. These are only the questions we have in heat energy. You can go to anywhere online, browse more questions under heat energy, then apply the knowledge gained from this class and others, maybe from other books, to unravel the mystery and come up from where you are getting those questions from. And again, if you have any questions to ask, you can do it in our comment section. And please don't the start of 7 when you are watching our videos. Guess there's anything here you don't understand, go back again, watch the video over and over again. More understanding will be coming up. So thank you. See you guys in our next class. God will bless you. Thank you. Thank you.